path integrals and states in quantum field theory. To set the stage, let me remind you how it works in the harmonic oscillator. So in the harmonic oscillator, the path integral calculates the transition amplitude. Well, I'm really not going to use the harmonic oscillator here, just ordinary quantum mechanics, but for example, the harmonic oscillator. Brought my own erasers. I know you wanted to watch me trying to use that rag again. Okay, so the transition amplitude from position x1 in time t with Hamiltonian h to position x2 is the sum over paths, obviously from x1 to x2 of e to the I s of x of t divided by h bar. And this is the standard Lorentzian signature path integral that you're used to from quantum mechanics. So remember that Lorentzian path integrals calculate transition amplitudes between quantum states. And secondly, remember that the wave function in the state psi is, by definition, psi of x is the overlap. So the wave function in the position representation is the overlap of the state psi with the position state x. So the transition amplitude that's calculated by this path integral is also, we can write in terms of the wave function. This is the wave function psi of x2 at time t in the state x1. Okay. So Lorentzian path integrals calculate overlaps, or you could say they calculate wave functions. That was quantum mechanics. Now let's do Q of t. By Q of t, I mean that by Q of t, I mean that we're setting Newton's constant to 0. Okay, so Q of t as opposed to quantum gravity. However, I will allow a general curved space-time. So that's a subject which people call Q of t in curved space. And although there are a lot of differences when you actually go to calculate things are harder in curved space. The basic formalism, the basic ideas of quantum field theory all carry over and still apply. Okay, so again, the Lorentzian path integral calculates the transition amplitude, but now the quantum states are specified by fields. So I'm just going to repeat what I did for the harmonic oscillator. Now we have a transition amplitude the states so the way I'm writing these states, I'll call by phi, I really mean all the fields. So we have to specify all the fields. And by vector x, I mean space only, not time. Okay, so the basis that I'm using is the field basis, where you specify the fields everywhere in space at a given time. And then we can calculate, so this state is the analog of just x1 in quantum mechanics. So then we can calculate transition amplitudes by the Lorentzian path integral. So this is the integral, the path integral d phi, where we put boundary conditions that phi at t equals 0 is equal to phi 1, and phi at t equals big T is equal to phi 2, and then we integrate e to the I s of phi. Okay, I get tired of writing those path integrals real quick, so I'm going to draw pictures of them. We're going to have about 1 million pictures like this in this course. So this is just a picture that represents this path integral. I've drawn a little piece of space-time here, and this picture tells us that at the bottom we impose the boundary condition phi 1. Remember, x is just space, so we impose the boundary condition that sets the quantum fields to phi 1 at this boundary. The boundary at the top of this partial space is boundary condition phi 2. And this is a segment of Minkowski space with Lorentzian time big T. Okay, does that make sense? This picture means this integral. We don't usually talk about wave functions very much in quantum field theory, but we can if we feel like it. And just as in quantum mechanics, this is a wave functional phi psi of phi 2 of x at time t in the state phi 1. This wave functional satisfies the functional Schrödinger equation by construction. Questions so far? Somewhere in the room, there's a clipboard going around. I'm asking people to put in your email if you want to get emails about the class. And also, I'm asking people to initial if you're okay with accidentally having your voice on the video, because I need people's permission, because I want to take videos. Okay.
Wait, so you're representing this amplitude by a capital psi?
It's not that I'm, this amplitude here, this is basically the definition of a wave function. So this is the wave functional, since we're doing quantum field theory, the wave function is a function of a function. So this is pretty much by definition the wave functional in state phi 1 at time t. Just like in the quantum mechanics case. Yeah.
Is this like a tensor network? With lots of flags?
This thing?
Yes.
Don't think about it that way.
Okay.
I mean, this is unitary evolution. So you can think of this as a quantum circuit if you want. But for most of quantum field theory and quantum gravity, that's not a very useful way of thinking about it, just because it's such a discrete thing to, it's so discrete, and quantum field theory is so continuous. So I wouldn't think about it that way, but it is sort of. It's a continuous version of that. Anything else? Okay, so that's a Lorentzian path integral. taken quantum field theory, you've also seen Euclidean signature, but the way it's usually introduced is sort of mysterious, and then there's some mysterious steps, like Wick rotation, that relate the two. And so one of my main goals in the next lecture or two is to explain how Euclidean quantum field theory is related to Lorentzian quantum field theory, and how we use the two together. Okay, so let's turn to the Euclidean path integral. So again, we're calculating a transition amplitude, but now it's evolution by a non-unitary operator. Tau here is Euclidean time, since there's no I. This operator is non-unitary. But we can calculate that amplitude. And the basic rule of the path integral is that if this is given by the path integral with boundary conditions phi 1 and phi 2 of e to the minus s Euclidean. I'll also draw this as a cartoon. Okay, the cartoon looks about the same. There's a phi 1 at the bottom, a phi 2 at the top, but now at an evolution tau. But we just have to remember, okay, this diagram looks a lot like the previous one. We just have to remember or notice that this is a Euclidean, this is a segment of Euclidean space. That other one was a piece of Minkowski space. Okay, so these are not equal to each other. It's just that I don't really know how to draw the difference between Euclidean space and Minkowski space. We just have to remember this is a Euclidean time direction. The other one was a Lorentzian time direction. Okay, so Euclidean path integrals also compute transition amplitudes, but in imaginary time. It's better maybe not to think of them as amplitudes, but just as state overlaps. This is the overlap. So this thing corresponds to the boundary condition at the bottom. This is evolution by Euclidean imaginary time tau, and that calculates, the path integral calculates the overlap of that state with phi 2. Note the special role of the Hamiltonian. The Hamiltonian generates the evolution from one time slice to the next. So acting with the Hamiltonian sort of takes you infinitesimally up this diagram and builds up the Euclidean space. And when you exponentiate, you get the whole thing. Questions? I drew these diagrams as if we're studying a 1+1 dimensional theory, but it could be d-dimensional. Okay, then each of these slices is Rd minus 1, and the full Euclidean space is Rd. And if we can use the same kind of pictures and the same path integral formalism to study quantum field theories on more general spaces. So, for example, if space is the sphere, Sd minus 1, then we can draw a very similar picture for phi 2 e to the minus IH tau phi 1. We just change the shape of the manifold. Okay, so the difference between these pictures is what theory we're talking about. These theories can have the same local Lagrangian density, But in this case, the quantum states here were the quantum states of the quantum field theory on Rd minus 1. And here, these are the quantum states of the theory on a sphere. It's a different set of quantum states. It has a different spectrum. Lots of things can be different. But as far as our pictures goes, we just draw the picture on a different manifold. Okay. So now I want to talk about quantum states and how quantum states are related to the path integral. The basic statement is that cutting a path integral defines a quantum state. For example, there's one we just talked about. Let's define the state psi of tau to be e to the minus h tau times the field state phi 1 of x. We can represent this quantum state by a cut path integral. So what I mean by cutting it is the following. We do a path integral, integral d phi e to the minus se of phi, where at the bottom of the path integral we put boundary condition phi of t equals 0 is phi 1. And at the other end of the path integral, we don't put a boundary condition. We just leave it open, leave it unspecified. That's what I mean by cutting open the path integral. We leave some boundary conditions unspecified. As a diagram, we can represent this as a cut of my previous diagram. So we have boundary condition phi 1 at the bottom. And here I'll draw a wiggly line to represent the cut where the boundary condition is unspecified. And this has size tau.
Are all of those tau? The t equals 0 is also tau. The bottom.
Yeah, let's see. Well, this t was the coordinate. Let's call this TE for T Euclidean. T Euclidean is the coordinate, and tau is the amount of coordinate time that passes here. Yep.
Why are we doing this in Euclidean signature?
We could have done either one.
Okay. I guess at this point, are we supposed to understand why we did anything
What?
in Euclidean signature?
No, not yet.
Okay.
Not yet.
Okay.
Okay, so let's think about this for a minute. Okay, so this is sort of a weird thing to do. It's like a partially definite integral. But why does this make sense? Okay, what is a quantum state? A quantum state is a ket is a linear functional on bras that turns them into numbers. Okay, a quantum state is if we pick a basis like the x basis, or in this case the field basis, a quantum state is a functional on field data that turns field data into numbers. And that's exactly what an integral is that's missing an endpoint. This integral is a functional on boundary conditions that turns boundary conditions into numbers. And that's what this picture is. So what this picture is really telling you is it's telling you a recipe. Well, let me write that in words. So a quantum state you could think of as a linear functional on field data, spatial field data, I should say. And what this kind of path integral gives you is it gives you a recipe for calculating the overlaps of that state with field data. So in this case, it tells you how to calculate the wave functional of your state. The wave functional of this state, I should probably put a tau in there, a time tau, is what you get by now filling in that boundary condition by putting a phi 2 at the top. And getting the overlap that we calculated a couple minutes ago. Okay, so path integrals with open cuts are formal objects. You can think of them as functionals on boundary data. Yeah?
In what sense is that linear?
In the sense that it agrees with this equation. And well, it's defined on superpositions by linearity, much like this. So it's defined that way. Other questions? Okay, so we need to get used. This is probably unfamiliar to a lot of you, but it's a really useful way of thinking about path integrals. And I want to build up some intuition for this. We're going to do lots of applications, but let me quickly go through a couple examples. The examples are going to be cartoons, but then there'll be some calculations in the homework. So, as another example, let's define, well, the point of this example is to illustrate that any cut path integral defines a quantum state. Okay, so I'm going to define a quantum state called C. C is for crazy. And this is the quantum state defined by this path integral.
I think Ibrahim's question was non-trivial. I mean, if this were just an ordinary integral instead of a path integral, and you wanted to say that the top argument or the upper bound of the integral was a plus b, then you could write that up as like the integral from your lower bound to a plus the integral from a to b. But you couldn't just say that it's like lower bound to a plus lower bound to b.
You don't put the a plus b up there. You don't. The superposition of the state phi 1 and the state phi 2 is not the state phi 1 plus phi 2,
Okay, good.
right? It's
Yeah.
different.
Right.
So it really is just defined by linearity.
Okay.
Could you explain that more? Why you can't just put a plus b at the top of the integral?
Because so I've chosen a basis, this field. I've chosen a basis here, but we could talk about other states. Like if we pick a particular phi 1 and phi 2, then this is a state that we can talk about. But this is not the same as just adding the field data. Just as in the harmonic oscillator, the superposition of being at x1 and x2 is not the same as being at x1 plus x2. The plus doesn't come out. Other questions? Yeah.
Sorry, wait, so if you project, let's say you project both sides of that equation onto a basis, wouldn't that, maybe you're wrong.
You mean of this equation?
No, like, of the first two lines, because you're defining a state is equal to that. And then you project onto a basis, and you get the sum of their projections, which is the sum of their wave functions.
Yeah, the wave functions add. Functions add. That's true.
Oh, right, yeah, you're not talking about wave functionals, you're talking about,
The boundary conditions
yeah,
themselves do
okay,
not add.
Yeah, never mind then.
Yeah. Okay, so any path, sorry, yes.
But when will we add the boundary condition? I mean, I never seem to encounter a case where we need to add the bras. Like, by saying that it's a linear functional, I suppose you mean that sometimes we want to add phi 1 and phi 2, which are those bras.
Yeah, that's right. Yeah.
But why is that useful?
Why is it useful to? Well, it's useful for the following reason. So when we talk about path integrals, this is true also of the harmonic oscillator, but in particular in QFT. When we talk about path integrals, it's most convenient for path integrals to work in a position basis. Okay, because we think of the boundary conditions on the path integral as being some position at time 0 and some other position at time t, or in the case of field theory, some particular field configuration at time 0 and t. But that's just a choice of basis. That's like choosing the x basis in the harmonic oscillator. And you need to be able to do quantum mechanics in any basis. You might want to go to the momentum basis. You might want to go to some other basis. So we have to be able to talk about superpositions of the phi 1s in order to go to another basis.
Yeah, I mean, the superposition is that when we were defining the state, we used the superposition of the basis to define the state.
Yes.
But then when you're saying that the side there is a functional, it has only argument phi 2 and tau, and so I think you mean it's a linear functional in phi 2, but that doesn't seem to be very useful.
What doesn't seem to be very useful?
So you're saying the psi is a linear functional on the field data phi 2.
Yeah, that's right. So that just means that phi 2 plus phi 2 prime psi has the sum of the wave functions just add.
But is this expression useful?
The fact that the wave functions add? Yes, it's definitely useful because it's important to keep in mind that just because we're using path integrals doesn't mean we're still just doing quantum mechanics. Okay, the path integrals they're our tool for doing quantum mechanics, but it's still just quantum mechanics. Even when we're doing QFT, it's still just quantum mechanics. And physical and states are vectors in Hilbert space, and we need to be able to talk about superpositions of those states to be able to do quantum mechanics.
Yeah, exactly. But
It's just that the path integral is most suited for a particular basis, but then we need to be able to talk about other bases as well.
Yeah.
So I don't know what you mean by is it useful? Yes, it's useful. Superpositions are essential for doing quantum mechanics, so we have to be able to do that.
But I mean, physically, if you think about quantum mechanics, so if you think about phi 2 and phi 2 prime as x and x prime,
Yes.
then it means we're adding the wave function at point, the amplitude at x and amplitude at x prime. So I don't feel that's very.
No, you're adding the quantum state, which is like a definite position basis state of x1 plus the definite position basis state of x2.
Yeah, you can understand it as overlapping of two states. Yeah.
Well, you're not taking the overlap of them, you're adding them together.
Well, in this case, I was taking the overlap with a state psi. I mean, at this point, I'm just saying you can do this,
Yeah.
and this is how you would deal with superpositions. Maybe we should just leave it at that for now. You can do this, and if you want to be able to deal with superpositions, that's what you do. Okay, so anytime you cut open a path integral, you define a quantum state. And so this is my state crazy, C for crazy. So this is a weird looking Riemann surface with a hole. So this is a quantum state in a two-dimensional quantum field theory. And it's a quantum state on the cut. So this is a quantum state on S1 in a two-dimensional quantum field theory. This is some crazy state in a d equals 2 QFT. How do I know it's a quantum state? Well, because I can calculate its wave function. The wave function of the state C in the field basis is what you get by doing the path integral with boundary condition phi of x on this cut. Okay, so that's the sense in which defines the quantum state. It's a linear functional on field data defined by doing the path integral. Yeah.
So if I compare the crazy drawing with the standard one, where is the initial data, the crazy one? Like there has to be a phi 1 or a C, I guess, like initial data from where you integrate towards the hole.
Yeah, good. There isn't. This defines a state. I didn't have to give any initial data.
Okay.
In that case, in that case, there was this boundary here, so I had to give you some initial data. But think of the shape of this thing as being your initial data here. You just do the path integral, and this is now completely well defined. There are no other holes left open, so we don't have to specify any more data.
What goes in the lower boundary integral then?
Of this path integral?
Yeah.
Well, this is a path integral on a manifold with only one. So there isn't a lower bound, because what we're doing is we're integrating fields that live on this manifold. Okay, so we're integrating the path integral d phi, where at each point on this manifold we allow phi to be anything. That's what we're integrating over. But we don't have to specify any other boundary conditions to do that integral. It doesn't have any other openings.
So your manifold also includes time, and that's a space-time manifold.
This is a Euclidean manifold.
Yes.
You should think of it as including Euclidean time if you want. But
yeah, I'm just thinking about the time arrow on the previous one. Like from here to here, there's a time somewhere there.
Yeah, that's right. These are both, well, there isn't really a preferred time in Euclidean signature. We're going to keep talking about that. But yes, this is a Euclidean space-time.
Okay.
Yes.
So x there is, like x vector is x and tau, just two coordinates on the manifold.
In this case, no. So when we do the path integral, we do the path integral, which is defined on as phi as a function of two coordinates. So that's phi everywhere on this two manifold. But when we specify boundary, these are the boundary conditions for the path integral. And the boundary conditions for the path integral have one less dimension. So here, probably my notation is confusing because vector x looks bigger than x. Vector x just means space. And I'm using x to be the full thing. So in 1 + 1 dimensions, vector x is smaller than x. Sorry. Yeah.
I don't know. What restrictions are there on where we make our cut? So what if we made our cut through the hole? So it almost looks like there's two.
Like if we, yeah. So what if we took this and we decided to cut it here? Is that the kind of thing you have in mind?
Yeah.
Okay, so you're perfectly free to define that path integral, but that's not a quantum state. And the reason that's not a quantum state is because when you cut on something like that, you actually get two boundaries instead of one. Okay, and well, I guess you could call, so this is either a state in two copies of the theory. Okay, because you have to specify two boundary conditions to be able to finish this path integral. So this is a state in two copies of the theory. Or you can think of this as an operator. Because what is an operator? An operator is something with two openings, one on each side. And I'll come back to examples of this, in particular operators. But for now, let me just say this has two openings, so it's an operator, one for each side of the operator.
Question?
Yeah.
If I deform this Riemann surface into some other surface, will it necessarily correspond to a different state?
Sorry, say it again?
If I deform this Riemann surface into a different surface, will it necessarily correspond to a different state?
Not necessarily, no. This is the choice of two-handled surfaces is probably, actually, I doubt that's a nice basis. It's probably overcomplete, or it might be, actually, I have no idea where this lives in the space of all possible states. Generically, deformations of this will give you a different state, but I won't guarantee that they're all different.
So like I can't make any statement like that this map from cut path integrals to states is like injective or surjective?
Generally, no. I'll have more to say about that when we start inserting operators, but generally, no. Yeah.
I think it was something similar to what he was asking, but what about the correspondence between states and operators? Conformal field theory, specific conformal field theories.
Yeah, I'll come back to that later, but let me just give the 2-second answer to your question. In conformal field theory, we can define quantum states, and we get a complete orthonormal basis of quantum states by inserting an operator and then cutting the path integral on the unit disk. That's the state operator correspondence. We'll come back to that. Yeah.
So the picture that you're sort of finding, so with that extra cut, so you have two you have two holes, right? So if you went to the picture above that and you sort of like made a cut on the other end, yeah, so something like that. Wouldn't that be the same as the picture on the right, on the other board? If you closed it up, you made it S1 instead of.
Yeah.
Yeah, you made it S1 and then you like somehow you put those genus whatever things in the middle.
Yeah, but you have to supply some boundary condition to make it look like the picture we did over here. So if I give you a phi 3, just not to confuse it with anything else we talked about, if I specified the boundary condition phi 3 on this cut, then this path integral now defines a perfectly good quantum state on that cut. And that's similar to the fact that if I have an operator O, and I supply a left-hand side to that operator, well, maybe I should put it on the right. If I supply a right-hand side to that operator, now this thing defines a state. So if you take an operator and you supply one of its legs with an input, you get a state.
Okay, so I guess my question is, why not just give those like phi 1 and phi 2, and like not think of those as being somehow like being produced by a single cut?
You mean here?
Yeah.
You want to put a phi 1 and phi 2 there?
Yeah.
Yeah, you can do that. Then this calculates the overlap phi 1, O, phi 2.
Okay.
Yeah.
Okay, in the top picture, can you like label the cut on the left or something for me, just so I could like ask my question? And
Bob.
okay, so if we let's say we integrate over Bob.
You
would
mean
that-
over the boundary conditions on?
Yeah.
on Bob?
Would that give us the original thing? Like the original state we had without the left cut?
You're trying to do something that closes this cut?
Yeah, by integrating over. So you would have kind of like, I guess, two paths, not one path.
That's a little complicated. The answer is there isn't generally a way of doing that, or at least not an easy way of doing that. There's some particular state you have to supply to this leg in order for this to agree with the smooth path integral that we started with. And finding that state might be hard.
Okay, I don't understand, because in the original one, you're integrating over all of the fields that could be at that place where you put the conjugate.
Yeah, good. Okay, this is running me into some subtleties here. Well, there's the question is, if you're going to do this cut, then yes, there's some way of integrating over all possible boundary conditions here, but the question is with what weighting? And the answer is, well, it's probably better just to erase the cut and do the original path integral. So I think that's in general the best answer to your question.
I'm not sure I see the difference.
Let's come back to it at the end, maybe we can discuss. Okay. Now, a comment at this point is that the last few path integrals that I've written up here are Euclidean path integrals, but they define states. Well, let me say a general thing first, which is that the Euclidean quantum field theory and the Lorentzian quantum field theory are not two different things. There's one quantum field theory. At least this is how I like to think about it. Different people think about this a little differently. How I like to think about it, there's one quantum field theory, and Lorentzian and Euclidean path integrals calculate different things in that quantum field theory. Okay, so in particular, I'm drawing all these Euclidean pictures, but these Euclidean pictures that I'm drawing define states in the physical, real-time Lorentzian theory, the one that we live in. Well, if we happen to live in 2 dimensions or whatever field theory we're writing. Okay, so in particular, just to emphasize this, we can take our state C and evolve it in Lorentzian time. It's a state in the quantum field theory, and one that can undergo ordinary time evolution. There's a path integral that does that evolution for us, and it looks something like this. with the caveat that this piece of the manifold is a Euclidean manifold, and this piece of the manifold is a Lorentzian manifold. What do I mean by that in practice? I mean, when you actually do the integral, remember, all these pictures I'm drawing are not just for fun, these are integrals. Every one of these pictures is an integral. Okay, so what I mean is that when you actually do the integral, here you do the integral e to the minus se, and here you do the integral e to the is. But the two manifolds are glued together along a circle. That is, there's a boundary condition that says that the field data on this Lorentzian manifold on this circle of this Lorentzian manifold at time 0 is equal to the field data on our Euclidean manifold at what used to be the cut. So if you like, you could think of this as sort of a mixed signature manifold, or you could think of it as a Euclidean manifold that's been glued to a Lorentzian manifold. What do I mean by glued? By glued just means that the fields are continuous as you travel from one into the other.
Do you have to do that at t equals 0?
It's convenient to call it t equals 0, I would say. You can do that. Well, if your starting point is Euclidean manifold, you can cut it anywhere you please and draw a Lorentzian manifold springing out of it. However, there is a restriction, because any Lorentzian manifold that you draw by doing that is going to have a time reflection symmetry around the quantum state that you define that way is going to have a reflection symmetry around the gluing point. So we can also take this quantum state and we can evolve it backwards in Lorentzian time, down that way. Now, I don't know much about this quantum state that we define this way. It's called crazy for a reason. But I do know that it's time reflection symmetric. So there's only special states that you can prepare this way with a Euclidean manifold. Yeah.
If you write out the integral for this, so this is it one integral for e to the power minus se, then one for is, and is there another part for the Boolean? Or
that's a convenient way to write it. You want me to write it? I could write it. That's a convenient way to write it. So a convenient way to write it is to declare that there's some data phi1 on the gluing, and then to integrate over phi1, integral d phi with boundary condition phi1, e to the is, integral d phi with boundary condition 1, e to the minus se. If we wanted to, we could have just said that we're doing this whole integral with the condition that they're continuous, but it's nice to say it this way. Yeah.
Is this not the same, something like this, is that not the same as gluing up the patch on the right? Or no? Like,
yeah, it's a lot. Yeah, it's a lot like that. Yeah, just gluing two circles together, and gluing two circles together means specifying the same data on both and then summing over that data.
I mean, the top picture, our previous discussion about filling in the left cut.
No, no, it's more like this. It's like gluing these together. Here you had one cut, and we were filling it into nothing, and left with no cuts. Here, this is still a quantum state that we're talking about, so there's still an opening up here. Okay, I can now sort of state what is, if there's a punchline here, maybe this is the punchline. Okay, and this is a rule of thumb for thinking about it, which is good to keep in mind. So repeat this to yourself. The Euclidean path integral prepares a state, and the Lorentzian path integral evolves in T. Now the Euclidean path integral evolves in Euclidean time, so I don't want to. There's a little bit of fuzziness in the difference between these, but this is the way to think about it. So Euclidean path integrals, nothing's happening in the Euclidean path integral, right? Like physics isn't happening. You shouldn't think of stuff like moving or going places in a Euclidean path integral. You should just think of it as a trick that prepares a state for you, okay? And then it's in the Lorentzian path integral that physics is happening. Okay, that's evolving in T. So a lot of times we do both kinds of path integrals, all part of the same calculation, but you think of the Euclidean piece of the path integral as preparing the quantum state, and the Lorentzian piece of the path integral as the physics happening. Okay, yeah.
But this isn't always true, because sometimes we just start with the Euclidean path integral because it's easier than the interpretation to get something Lorentzian.
We'll come to that, but I think that fits into this. Yes.
In that first example where you specify the state along the boundary, even Euclidean, or like, tau goes to minus Euclidean time, why can't one just specify some boundary conditions and then just evolve in the Lorentzian time? Why go through this Euclidean?
You can, yeah. The first example, I think we could do it. Well, I just happened to write that example in Euclidean. We could have done it in Lorentzian.
Right. I mean, if we're okay with specifying boundary conditions in Euclidean signature as well, why not just specify boundary conditions in some Lorentzian time and just evolve with the Lorentzian?
Good. Okay, that's the right question. So let me repeat the question. The question is, why bother with this? Like, why? If we could just define if we could just do everything in Lorentzian, why do we need to prepare states in Euclidean? If we could just do everything in Lorentzian and specify some initial data in Lorentzian. Okay, good. The answer to that question is that very often Euclidean path integrals prepare really great states that we like. Okay. And we're going to see lots of examples of this. This will come when we start talking about Unruh radiation and black hole radiation. Euclidean path integrals will be the right way to think about it. Even in the vacuum state, as I think we'll come to in a couple minutes, the Euclidean path integral is really good at preparing the vacuum state, and that makes it useful for calculating, for example, scattering amplitudes.
So by really good, you mean there's no other way that I could specify the same state?
There's always another way. Well, not always. There's always another way in principle, but quite often the Euclidean path integral is by far the best way of thinking about it. And that's especially true when we get to gravity. So yeah, another like general words. All these pictures and everything, I think these are a good way to think about quantum field theory and really useful. But the real power comes in when we turn to quantum gravity. Okay, so Euclidean path integrals and these kinds of tricks are good tricks for quantum field theory, but they're really totally essential tools for quantum gravity that give us information that we can't get any other way. And that's a bit of a mystery, actually. There should be another way, but in many cases, it's the best we have. Yeah?
So I just don't remember something. So the relation between these two ways of doing things is just analytical continuation, right? Like you say that your time t is t plus imaginary number tau, and then you evolve in tau instead of t.
Well, that's sort of true. That is true in vacuum, and I'm going to have more to say about that, but there isn't a tau here. I mean, there is no symmetry. There's no translation symmetry in a direction that we could call tau on this manifold. So there is no sense in which you can get from here to there by sending tau to IT like we do in Wick rotation. The reason that works, well, I'm going to come back to that point of view for and how we do scattering amplitudes and stuff. But let's come to that. Did that answer your question?
It will.
For now.
soon.
Okay, yes.
Okay.
Good. Other questions?
Okay, so the things that we can't do it locally, like we can put these coordinates such that there is, Euclidean time, like locally on this manifold.
Yes,
Okay.
that's right. But what people are referring to is Wick rotation in quantum field theory, which is only sometimes justified and is not justified in this case.
But this is crazy, right? So
What's crazy?
that's
That state?
Yeah.
Well, it's a state, yeah. And there will be other cases that aren't so crazy, where you also don't have that option.
Okay.
None
Yeah.
of this has used the metric yet, right?
True, yes.
Wait, really? Didn't you have to use the metric to integrate?
Oh, well, sorry, it depends what you mean by use the metric.
Oh.
Yes, the metric is in all these integrals.
Okay.
It's a fixed non-dynamical metric. None of this has used gravity in it.
So does the signature of the metric somehow change across that like Euclidean?
Yes.
set?
Yes, it does. It does. And that's built into the fact that the ordinary Lorentzian action is one with a Lorentzian signature metric, and the Euclidean action is one with the Euclidean signature metric.
So is this like a physical space in any way? Like,
This one?
well, like the whole construction? Like,
I would think of this as a trick to make a quantum state.
okay, but like if you were to write this down in like our universe in some way, like how can the like signature of the metric like change just continuously like a patch of space?
But remember that Euclidean path integrals don't happen. They aren't things that happen. Okay, so this picture is not something that you should think of as happening.
Okay.
You should think of like this part of the picture as being some trick that you do to
Okay.
cook up a state, and then experiments and stuff are all up here.
Okay, so only half this picture is like real in any sense?
Yes.
Okay.
Yes. Okay. Yeah.
Is the time reflection symmetry just a result of the fact that the time derivative is squared in the Lagrangian?
Well, I haven't given you a Lagrangian.
Is it just quantum mechanics being time reversal embedding?
Yeah, it's really just that. Yeah. I think.
Well, in this case, it
Yeah.
does not do with the underlying manifold. In fact, that was like static stuff. Really back into the
I think I'll have more to say. I don't want to get stuck on this, and it's confusing me. But locally near here, we can send tau to IT or to minus IT, and nothing's picking for us. Okay, so that's basically what it is. But let me not get stuck on trying to explain it better than that. Maybe we can talk about it after. Yeah.
So, basic question. So if I wanted to create the ground state of a harmonic oscillator using the
Ground state's next.
Oh, okay, good.
Let's do the ground state. I started with the crazy states. I don't know why. They were more fun. So example 3 is the ground state. So we could take any state and expand it in energy eigenstates, where H on N is the energy. And Euclidean evolution damps the excitations. that is e to the minus tau h on this arbitrary state big Y. Well, we can just bring that inside the sum, and we see that it becomes e to the minus tau E0 on vacuum as tau goes to infinity. That is, the lowest energy state is ultimately the only one that survives under a large amount of Euclidean evolution. So Euclidean evolution damps excitations. Therefore, the ground state, 0, is equal to this path integral. Where now, instead of putting some field data on the lower cut, I've just let it go off to infinity. To be clear here, this is a Euclidean manifold. So this manifold is, so what this picture means is the Euclidean path integral e to the minus se on half a real line times rd minus 1. Okay, the half real line meaning the negative half plane here. But the integral just goes down all the way to infinity.
And it doesn't matter what data you specify at infinity.
That's right. It doesn't matter what we put down here, because whatever we put is going to get damped by the infinite amount of Euclidean evolution. The only thing we have to, the only boundary condition we need to put at tau equals minus infinity is regularity. If we put something infinite there, then it might not get damped away. But as long as it's regular, we're good. Yeah.
Oh yeah, he was about to say, if you put like a third energy eigenstate, like one of the other ones, then that would just get killed, right?
But on field, right? That's right. I meant on the field data.
Yeah.
That's not a field configure. The energy eigenstate won't be a field configure. Well,
what do you mean by that?
I guess that depends on the Hamiltonian. In any reasonable Hamiltonian, that won't be one of the field states. In this, it won't be in this basis. So if we're just talking about doing the path integral with some fields phi, then we typically don't have to worry about that.
Wait, what's the concern?
The concern is if down here we put like something that didn't have any vacuum state in it, then we would get the wrong answer. We'd never have to worry about that. I think there are some exceptions. I think there's some weird quantum field theories in 1+1 dimensions where you might have to worry about that, but you almost never come across them in QFT. Yeah.
This is all up to an overall constant, right?
Yeah, good. I was going to mention that. These are unnormalized. And that's actually going to work to our advantage pretty soon. As usual, pictures like this are valid for the QFT on any space. Okay, so the ground state on S1, let's say, for d equals 2, is 0. I'll write the subscript to indicate that we're talking about quantum states on S1. is the path integral on the semi-infinite cylinder, the Euclidean semi-infinite cylinder. Quick point of clarification, sometimes when people talk about putting a quantum field theory on a manifold, they're talking about a space-time manifold, and sometimes they're talking about a space manifold, and this can get very confusing. Okay, so let me clarify. When you talk about the states of a quantum field theory, that only cares about space. Okay, so if I ask what are the states of a quantum field theory on S1, a two-dimensional quantum field theory on S1, that's a good question to ask, because the space of states depends only on the Hamiltonian and the fields and the boundary conditions on those fields, and that's something that you specify in space.
Of course, you're free to pick different like, space-like displacement. If you're in a space-time.
Yes, but it's a good, right, that's true. I can relate different spaces by symmetries, but it's a good well-posed question if I say, what is the space of states of this two-dimensional theory on S1? That's the right way of thinking about it. Now we can put a quantum field theory on a cylinder, a two-dimensional quantum field theory on a two-dimensional cylinder. But now I'm not just talking about the states, now I'm talking about the whole path integral somehow, and people often use that language. Okay, so the way to the language sometimes is space and sometimes is space-time. But if we're talking about the states, then all I have to specify is space. And then the matter of space-time is, what do you do to those states? Do you evolve them with one Hamiltonian or another Hamiltonian? Do you evolve them in Lorentzian or Euclidean? That's all space-time questions.
You said path integral?
What?
You said, doesn't the path integral correspond to a state, or is it just cut path integral?
So good. Anytime you have a path integral, you can cut it, and that gives you a state. The converse is only sort of true, and I'm going to have something to say about that in a minute, I think. Well, maybe next time. Let's see. Is it 2:10? Okay. In the last 5 minutes, let me start talking about operators. So I just want to put correlation. So